everyone, welcome to another lecture on LLMs, and this is very important because in this lecture we are going to discuss how we can align LLMs with human feedback, right? And this is one of the major research interests these days, how to make LLMs human like, and and so on and so forth. So in this lecture we will discuss after instruction fine tuning, what else we can do to make these LLMs human like. Of course, in terms of responses, right? The responses should be unbiased, should be fair, should be non-toxic, should be human like, right? And we will discuss few specific approaches, right, which are mostly motivated by reinforcement learning, and how we can incorporate human preferences into the learning paradigm. Okay, so far what we have discussed, so we have discussed pre-training methods, different pre-training methods, specifically encoder only, decoder only, encoder decoder models. We have seen pre-training methods like masking words in case of encoder only model. In case of decoder models, predicting the next word, autoregressive kind of setup, and so on. And in the pre-training phase, we essentially teach the model what are the basic the basic components or basic aspects of a language, right? So once the pre-training is done, the hope is that the language model understands nitty-gritties of a language, right? But the language model doesn't know how to respond to a query, right? Let's say you write some instruction, language model doesn't know how to respond to that. So for that, we discussed instruction fine tuning, where we have essentially instructions for different tasks. Task can be summarization, task can be machine translation, task can be, let's say, textual entailment, or so on and so forth, where we have instructions and the corresponding responses, right? A pair of sentences. So we have instruction as a sentence, or let's say multiple sentences as an instruction. You also have corresponding response for that instruction, and you teach the model how, given an instruction, the model should respond, right? The problem here in instruction fine tuning is that although the model learns how to respond to an instruction, but the model may not be able to respond in such a way that a human responds, right? For example, let's say if I ask that can you give me the glass of water, right, to the model. If the model says yes, I can, right? So that's not the right answer that we can expect, right? What we expect is that the answer should be yes, here it is, right? Or let's say, can you tell me the time? If you say that yes, I can, that's not the answer. The answer should be yes, the time is, let's say, 3 p.m. or 4 p.m., right? So the model knows how to respond, but the model may not know what would be the appropriate response for an instruction, right? So in today's lecture, we will essentially discuss how we can align machine's response to the way human basically responds, right? So what we will do, we will see how we can take feedback from human, right? And we can refine the model further and further. On top of this instruction fine tuning, we refine the model further and further to make it more human like, right, in terms of response generation. Okay, so let's take another example. Let's say if the question is, what's the best way to lose weight quickly, right? If we say that you should stop eating entirely for a few days, that is not the solution that we expect, right? Because longer starvation would lead to some other diseases in your body, right? Instead of this, if you can say that, okay, you reduce your carb intake, increase fiber and protein content, increase you basically increase your regular activities, exercises, and so on and so forth, that would essentially be better response compared to this. Remember, both these responses can be generated by the LLM. So far, after instruction fine tuning, the model doesn't know which one is better, this one or that one. right? So in human feedback, we will essentially let the model know that you should essentially respond this rather than responding this, right? So alignment can basically prevent certain outputs that the model assumes to be correct but humans consider wrong, right? For example, this one. Okay, so now alignment, if you look at the taxonomy or classification, different types of alignments, you can broadly classify them based on the alignment objective and based on whether they are essentially being executed online or offline, right? So alignment objective, if you look at a pure reward maximization based approach, don't worry about what reward is and so on and so, we'll just discuss all these things in today's lecture, right? But if we go with reward maximization, then we have methods like PPO, right? PPO, I mean, these days we call this as RLHF PPO. And then we have another type of methods called constructive learning, and DPO, the direct preference optimization, actually comes under some sort of contrastive learning, right? And then DPO is actually an advanced version of PPO. We may not be able to cover DPO in this lecture, but you can essentially look at the paper, and there are many other online materials available. So this basically follows contrastive learning paradigm. And then we have another type of methods called distribution matching. Again, these are advanced methods like brain and DPG and stuff like that. Whereas if you look at the other aspect, whether we do it online, in the sense like let's say you give a feedback, and then based on the feedback the model gets updated, you further the model generates something, again you give feedback, and you keeps on updating the model again and again with different iterations, right? So this is called online kind of alignment. Whereas offline, you will not do this iterative process again and again. You have some outputs from the model, you do all this offline computation, and then in one go essentially you further modify learning process of the model. And then we have a mix of both online and offline, which is more of an iterative DPO and the brain model, the brain method that I was talking about. So in this lecture we will primarily focus on reward maximization based method, PPO, proximal policy optimization, which is also an online method. Okay, so as the name suggests, you have heard of the term like reward, right? Policy. And as you may imagine that this concept is related to reinforcement learning, right? Again, this class, in this class we will not discuss reinforcement learning. You can take other courses to understand RL better, but I will try to give you a very, very high level overview of reinforcement learning just to set the context clearly. Okay, so in reinforcement learning, we all know that it basically follows something called exploration exploitation mechanism, right? You explore something and then all the explored things will further be exploited, right? So in reinforcement learning there is a policy, right? And this policy essentially determines what is going to be your action. Think of a blind person, right? A person who cannot see, right? A blind person is, let's say, walking on a floor, and he doesn't know how to let's say how to take the lift or how to follow the stairs, right? So what he will do, he will essentially explore different ways to essentially go to the lift, or different ways to go to the stairs, right? He may not be successful in the first term, the second term, third term, but eventually over time he will essentially learn which path to follow to go to essentially the lift, right? And how to press lift's button and so on and so forth, right? Here exactly the same process will be followed. We have a policy model. Now the name policy may look a bit cryptic, but you just think of it as a normal model, right? What it does, given a state, so you think of as I was talking about this, the blind person walking on the floor, right? Whenever he takes a step, right, or takes an action, he actually moves to another place, right? Let's say turn right, right, and he moves to the right side corridor. Turn left, he moves to the right left side corridor, and stuff like that. So every action that moving to the left is an action, and when he moved, that is basically going to change his state, right? So earlier he was at this position, now he is in the he's at this position, right? So a state got changed from here to there, right, because of this movement, left side movement. Here also, for this policy model, right, there are different states. For example, at tth time is t is the state, right? Now given this state, if you take an action, right, that would lead to another state, right, that would lead to a state like is t plus 1, right? Now you may have seen this kind of diagrams in theory of computation, automata theory, right, where there are basically finite state automata, different states, different actions. Each action leads a state from the previous one to the current one, and stuff like that. Here the process, the concept is exactly the same. You have different states, you have a set of actions, right? The set of actions is finite, mostly finite, right? And essentially you learn all these states through different actions, and overall, and I mean at the end of the day, you know that which set of actions essentially to follow to essentially reach a certain state, right? So here the policy model is nothing but our own LLM, right? It's a large language model, okay? It's a language model, right? And what is the state? The state is whatever responses the model has generated so far, right? Let's say the prompt is what is the capital of India, right? This is the prompt. Now the model generates the capital of India is Delhi, right? So when the model generates that's a state, right? And because of that state, right, so after that state we will have some action, right? So let's say you have an action, and the action is to choose the next word, and the next word is let's say, let me write, so the capital of India is Delhi, right? So you have a prompt that is given to the input, that is given to the model as input. The model generates this is state 0, right? And then based on certain action, right, let's say the model now generates this word capital, right? Now whatever we have so far, this is my current state, right? So then let's say this is state 1. So what is state 1? State 1 is the capital. Then the action says, the policy model dictates that the next action is going to be off, right? So the word off is generated. So the state so far is the capital of, right? And so on and so forth. Now, who says that at this place the word should be off? The word can also be is, the word can also be in, right? Remember, at this state, when the state is the capital, right, how many possible words that can be generated here? There are this, we have this vocabulary. Let's say the size of the vocabulary is mod v. Let's say the size is, let's say 50k vocabulary words. So any word essentially come here, right? So whether this is off or in or the, who will dictate this? Somebody needs to dictate this, right? So we will see that there is another model similar to policy model. There is another model called the reward model, right? Okay, and through this reward model, the policy model will learn that it should be off, not in. Okay. The example that I gave, this blind person, right? So let's say the blind person turned right and he got stuck at a door, right? And the door is closed, right? So he got hit, and that's a reward, right? So the reward can be negative, the reward can be positive, right? If the reward is negative, the model will not move to the right further, right? So the model will learn that if I move to the right, there might be there might be something which can essentially stuck the entire process. So I should not move to the right. Here also we'll have a reward model. We'll discuss what the reward model is, and based on that the model decides which action to take and which action we should not take, right? So we denote this policy as pi theta. Theta is the set of parameters, right? It's a large language models, so all the parameters are denoted by theta. St is the current state. Given the current state, you essentially generate an action, right? So essentially policy model is nothing but probability distribution over action space, right? In our case, action is essentially the vocabulary terms. So you essentially produce the distribution. The policy model produces a distribution, and based on the reward model, the policy model will learn which action to take, which action not to take, right? So what is ST? As I mentioned, ST can be the tokens of the input prompt instructions along with previously generated output tokens, right? So this is the prompt. The prompt is, as I mentioned, let's say this is the prompt, right? The prompt is what is the capital of India, and you have generated till this part. So from the beginning of the prompt till capital is going to be your state, right? That's going to be your ST. A is the action. A can be any output token generated by LLM. The policy captures the distribution over the output tokens given the prompt or the instruction, right? So this is the distribution. So till this part, you may wonder what is new, right? An encoder model, decoder model, a transformer model, they also generate they also generate the distribution at the output, right? What is interesting here is that the distribution is controlled by this reward model, right? And we will discuss this. Okay, so this is another example. A policy pi theta, right? St is the current state, A is the action. If you take an action AT, it will essentially lead to another state. For example, in this case, let's say the prompt is where is Taj Mahal assistant. Now this is my prompt, right? And you generate Taj Mahal as the output, right? So till this part, it is essentially, it will act as a state, right? So now this is important. So given a policy and an action AT, it will generate and it will basically move to another state, ST plus 1, right? So now in a traditional RL setup, let's say a robot is moving on the floor, right? And the robot is exploring all different avenues to essentially move out of the room. So the environment is the room, right? And robot will get stuck. It will get a reward, right? It will learn that, okay, I should not follow this, I should follow the other direction and stuff like that. So that's my environment. But in the context of LLM, right, there is no precise environment as such, right? There is no explicit environment as such, but the term environment is always important to understand. So whenever we draw this kind of diagram, we will keep this as as a standard notation for environment. But don't worry about environment for the time being, right? So in LLMs, in this aspect, there is no environment as such. So, and the other difference is that in this case, in the standard reinforcement learning, whenever you take an action and move to other state, you get a reward. But here, we will not get a reward until we'll basically generate the end of sentence. What does it mean? Let's say let's say what is the capital of India, right? So this is my state, this is my prompt, and this is my current state is 0, right? You give it to the model says that the, right, so this is my current state, so my current state is S1 till, so from what to the, right? So you expect that at this stage we get some reward, but we will not get any reward at this stage, because as I mentioned, we'll get the reward when we generate the end of sentence, right? So the capital of India is Delhi, then full stop, end of sentence, right? Here you basically get the reward. Okay, so that's the difference. So the policy, you take action 80, right? Environment, you explore the environment, through that you essentially move to state st plus 1. At st plus 1 you again take an action A, right? Explore the environment, you'll move to state s sub t plus 2, and so on and so forth, right? So where is Taj Mahal? It will generate Taj, reward is 0 because it is not the end of the sentence. Then Mahal, reward is 0 till this part. Is 0 reward, right? End of sentence, reward is plus 1, right? Agra, and the output is Agra, and then end of sentence, so and then plus 1 reward. Okay, so this is something that we should remember. All right, now let's talk about this reward model. Remember, we discussed something called the policy model. Okay, policy model essentially generates the next action, and based on the next action and the reward, based on the next action, it essentially moves to the next step, next state. So in reward model, right, now think about it. The reward model can, an ideal reward model should be a human being, right? What is the reward model? What is the intuition behind the reward model? So the reward model essentially says that you should not do this, you should do this, you should not do this, right? Let's say you generate that the capital of India is Mumbai, right? The reward model should say that this is wrong. Okay, so ideally you expect that there will be some human being who will essentially essentially say that this is correct or this is wrong, thumbs up, thumbs down, right? So ideally the reward model should be a human being. What is the challenge? Of course, the first challenge is that it is extremely costly, time consuming to employ human being to look at every output of a model, right? And remember, the feedback that you obtain from human or from the reward model, that gets fed to the model for further fine tuning. So human feedback is extremely costly, slow. So what we do is that we essentially use an LLM as a proxy of a reward model, another LLM which will act as a reward model. So human feedback is very costly. The second problem is that you essentially need the human being to be present at every iteration, at every step. Whenever the model generates something, that human being should essentially say that this is correct, this is wrong. Of course, you can think of a hybrid approach where some subset of the output generated by the model can be treated, can be annotated by humans, right? Whereas the rest of the outputs can be annotated by LLM's feedback and stuff like that. But essentially, in this kind of setup, we will use an LLM which will act as a reward model, from the beginning. So traditionally, the term that we use is RLHF, reinforcement learning from human feedback. Reinforcement learning from human feedback. RLHF, very standard term that people use in RL as well as in alignment. So the traditional RLHF requires humans to be there. What we do here, we replace this by an LLM, right? So we have a policy which is an LLM. We have a reward which is also an LLM, right? What is the task of this reward model? The task of the reward model is to guide the policy LLM that this response is bad, this response is good, right? Let's say given a prompt X, the model generates Y1. Remember, policy model is a probability distribution, right? It can generate ideally infinite number of responses that you can think of. Let's say the policy model says, policy model response returns Y1 in one iteration, Y2 in another iteration, right? For the same prompt. It can be possible because LLM is a stochastic process, right? It's a probabilistic process. So the reward model should say that Y1 is preferred, Y2 is not preferred, right? Ideally, this should be a human being, but since this is costly, now I am replacing a human with a reward model, with an LLM to act as a reward model, right? I hope the concept is clear till this part. Okay. So the next question is, how do we train this reward model? So we need to train the reward model such that the reward model will be able to say that given an X, which is a prompt, and two outputs Y1 and Y2, Y1 is better than Y2. Of course, we need human labels, but that is fine. By that, we will essentially consolidate a few such responses, right? And we will annotate this through via human feedback, and that annotations will be used to train this reward LLM, right? So essentially, what this reward model does, given an instruction S, which is a prompt, right? And a response generated by the policy model. So we have a policy model here. So the diagram should be like this. We have a policy model, policy LLM. X is the input. The model generates Y, right? And then we have this reward model, reward LLM. The reward LLM will say that the reward R, so the reward is denoted by R, X comma Y is, let's say, 0.7. Okay, let's say the reward value ranges between 0 to 1, and given X and Y, the model will say that this is 0.7. Okay, now think about this. So to train this reward LLM, what do we need as a training data? X1, Y1, X2, Y2, dot dot dot, Xn, Yn. These kind of pairs, right? And the number. How do you get these numbers? So these numbers will be obtained from humans, right? And these numbers are so subjective. Now, of course, for questions like what is the capital of India, what is the where is Taj Mahal located, these are factual questions. These are very easy to rate. Whereas more subjective questions, right? Let's say a poem or an essay, right? An opinion, right? It varies a lot, right? If we employ human being 1 versus human being 2 for the same set of pairs, you may see a completely different rating altogether. So rather than teaching the model to produce this score directly, what we can do, you can essentially teach the model to compare between Y1 and Y2 given an X, right? It is easy and it is less subjective. Okay, let's say The prompt is write a poem about the festivals in Delhi, right? This is the model generates y1 in one iteration. The policy model generates y1 as a response in one iteration and y2 as a response in another iteration for the same prompt, right? Now, if you ask a human being to basically rate which one is better, y1 or y2, it is easy for the human being to say that y1 is better than y2 or y2 is better than y1, rather than saying that the quality of y1 is 0.5 and the quality of y2 is 0.7, right? This number business is very difficult, right? Instead of this, I mean, it is easy to say that okay, y1 is better than y2. Okay, so this is the idea, and in this way we train this reward model. So given the same prompt X, two responses will be generated, y1 and y2. Who will generate the response? The responses can be generated by the policy model, or the responses can be generated by any models, right? What you essentially need this data set, right? You essentially need this one, x1, y11, y12. These are two outputs, and what else do you need? y11 is worse than y12, for example. Again, given another prompt x2, y21, y22, right? y21 is better than y22, something like that. You need this annotation. Doesn't matter whether y1, y11, y2, y12, y21, y22, all these outputs are generated by the policy model or any other LLMs that you can think of, right? So we'll discuss this thing later. So now when a human rates this one or the human annotates this one, which one is better, y1 or y2, right? This is called reinforcement learning with human feedback. If there is another LLM or another AI which will decide which one is better, y11 or y12, we will call this as RLHF, right? Reinforcement learning with AI feedback. Okay, so this is crazy, right? I mean, you replace reward model, the human-based reward model by an LLM-based reward model. Now you are saying that to generate the training data set for this reward model, I will use another AI model, maybe another LLM, to essentially rate which one is better. Nevertheless, I mean, and if you have, let's say, capacity in terms of deploying models, or let's say you don't have capacity but you have money to hire people, right? You can go with either RLHF or RLAIF, doesn't matter. Okay, so this is the structure of the reward model. As I mentioned, this is an LLM. It can be encoder model like BOT, Robota. It can be decoder model like let's say GPT or Llama or Mistral, whatever, right? What is the input to this model? The input is as follows. So I mean, now this is the model. This is the structure of the model. Okay, while training or inference, right? Let's say this is X, this is the instruction, and this is the output. You have some encoder blocks, decoder blocks, right? These are the embeddings of tokens after certain encoder blocks, decoder blocks, and then you either average all these tokens, right? Pass it through a linear layer. Now this linear layer can be trained, right? This can be trained with the data set that we talked about earlier, right? This will be trained, and the model should be able to say that for this X, the reward value of Y is this much, right? And stuff like that. So you train this linear layer from scratch, and of course you can fine tune other layers as required. Let's focus more on the reward model now. Okay, so what is the input to the reward model? Again, remember, reward model is an LLM. The input to the reward model is prompt, y1, y2, two outputs, and which one is better. This is the reward model. This is the data set for the reward model. And we need to train this model, so we should have some cost function, some loss function here at the end, which we will essentially back propagate, right? What is the cost function? Okay, so the cost function, I mean, I can just straight away write the cost function, which is very intuitive, but the cost function is essentially motivated by by a distribution called Bradley-Terry model. It's a Bradley-Terry model, BT model. It is essentially used when we have a pair of outputs and you compare pair of outputs, and we expect a distribution over a pair of outputs and stuff like that. Okay, so I will discuss Bradley-Terry model briefly, and then based on that we'll see how the reward model, I mean the loss function for the reward model is computed. Okay, so suppose that you have, let's say you have entities like y1, y2 dot 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 yn, right? And you have some sort of score associated with entities, and let's say these scores are preference scores, right? Remember, we are discussing Bradley-Terry model, and from Bradley-Terry we'll see how the cost function is derived. P1, P2 dot 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 Pn. If I ask you what is the probability that y1 is preferred, yi is preferred over yj, okay? If we follow Bradley-Terry model, it will say that I will prefer yi given yj. I will write in this way: yi. It's not the greater than symbol, by the way. Okay, there's a tilde. So there's a small tilde here. Okay, the probability is this: pi by pi plus pj. Okay, now if your model follows this distribution, you say that it essentially follows the BT preference model, right? Of course, you can make it more sophisticated. You can say that, okay, let me not use this, let me use something else. So instead of using pi, I will use exponential term, exponential of ri. What is ri? Ri is log of pi. This is exactly same, exponent log. So exponent log pi is essentially pi, right? So instead of writing this, I will write in terms of exponential, exponent ri by exponent ri plus rj, where ri is log of pi and rj is log of pj. So these are same, by the way. Now, given an input x, remember in our case we have the prompt as an input and outputs are y1 and i2. So given x, what is the probability given x? So given x, what is the probability that y1 is preferred than y2? Okay, so so what we do here, we will write in this way. So we'll write it in this way. So exponent of r star, I'll tell you what is what r star is. y1 x r star y2 x. Okay, what is this r star? R star is a kind of a it's an oracle reward function, right? Of course, it's a reward function, right? Right, as you see, r star, right? They're the same kind of, right? So r star r is ri, r star I, they are linked to pi pjs, right? Now pi pjs are what? Pi pjs are scores, right? How do you get the scores? The scores are something that are obtained from, let's say, some human feedback or some other from other some other models, right? So now R star is an arbitrary function. This is an arbitrary function. Okay. Now we do not know how do we get this R star, right? So then what we say is that, okay, let us parameterize this, right? Let us have some model theta which will essentially determine this R star. Okay. So instead of writing this, now I will write this one: exponential of R theta x comma y1 by exponential of R theta x comma y1 plus exponential of R theta x comma y2. Okay. What are the difference between this and these equations? So here we are using R star, which is a gold standard or gold label. So we do not know the gold label, right? Therefore, we parameterize this using some sort of model whose parameters are theta, right? And what is this theta? This is the reward model, right? This is the parameters of the reward model. So what is our aim? The aim is essentially to maximize this. Okay. So given a training data of the form x, y plus, y minus, x is the prompt, y plus is the preferred output, y minus is the non-preferred output. This is the same as y1, y2. I just write it in a different way. X, y plus, y minus. Our task is to find a reward model R theta, right? Which essentially and how do we get this? We maximize the log probability of preferences, a simple log likelihood estimate kind of paradigm that we follow here. So we take the log of this and we maximize this. This is my likelihood. We take the log of this and we maximize this. Very simple. So log of let me just erase this. Okay. So log of this, right, which is the likelihood for us, log of p theta, and p theta we already discussed. P theta is essentially exponential of this is p theta for me, right? So log of this, log of exponential of this by exponential of this plus this. We can further simplify this by dividing numerator and denominator by this. Okay, so this is like e to the power x by e to the power x1, e to the power x1 plus e to the power x2, something like that. Okay, if we divide it by e to the power x2, this is going to be e to the power x1 minus x2 by 1 plus e to the power x1 minus x2, right? This is exactly the same. Okay, now if you look at this very carefully, what is this? This is e to the power, right? Look at here. Only focus on this part. Okay, what is this? This is sigmoid, right? So log of sigmoid of this. Okay, so essentially we maximize it. We maximize the log sigmoid of the reward difference. We maximize the log sigmoid of the reward difference, and through the maximization, then we'll use standard gradient descent kind of approach to essentially update the model parameters theta, and we will will essentially get modified models over the iterations, right? So this is my objective function for the reward model. Given my training data x, y plus, y minus, I want to maximize this, maximizing the log sigmoid of the reward difference between the preferred and the unpreferred outputs. All right. So now we understood the reward model. So we have policy model, right? This is the policy model. This is the reward model. We know how to train the reward model, right? And remember the way we trained. So for training this, we need this pair x, y plus, y minus, right? But what is the output of the model during the inference stage? The output of the model is the reward r, right? And what is the function for this r? X, y. So during the inference, we don't need this pair y plus, y minus. Y plus, y minus is needed only to train the model, okay? But when the model gets trained, it knows that given a prompt and an output, what would be the reward value. So ultimately, the model will produce a number. But the way we train the model is not the way with the traditional model gets trained, right? So here we train the model using a pair of outputs. One is preferred, one is unpreferred, and through this the model knows how to score an output given a prompt, okay? So again, think of the high level picture. Given an input x, the model produces an output y. The reward model says that look, it is not a good output, 0.3 or 0.4. This will be fed to the policy model, and the policy model will get updated. So policy model again is an LLM, right? If you remember, we wrote pi theta, right? So all these theta parameters get updated. Okay. So to train this reward model, what do we need? We need x, y plus, y minus. What is x? X is the set of prompts, right? And how do you get these prompts? So one option is that you already have this instruction fine-tuned, you have the data set for instruction fine-tuning. The instruction fine-tuning, the data set looks like this. Summarize this, right? And the output. Translate this and the output. And so on and so forth. What you can do, you can essentially divide this instruction tuning data set into two parts. You keep one part for instruction fine tuning and the rest of the part for alignment. Or you can essentially let your model, let the users use your model the way ChatGPT did. So ChatGPT was announced, ChatGPT was given to public for usage. We people wrote a lot of prompts, right? And they used, OpenAI used these prompts for their RLHF. This can also be done. So X is sorted. How do we get this Y's, right? The Y's, as I mentioned, all these outputs can be generated by the instruction tuned LLMs, right? Which you are now, you are trying to align, or these Y's can be generated by any LLMs, right? How do you know that y plus is better, y minus is not better, right? Or y plus is preferred, y minus is not preferred? Either you employ humans, this will be RLHF, you employ AI as judge, and this will be RLAIF. Okay, so the models are, so the data sets are sorted. These are two publicly available data sets. If you are interested in this space for your research, you can use OpenAI's dataset, right? Which essentially looks like this. Summarize. So this is the prompt and the output, right? Prompt and the output, and they have human labeled dataset. Whereas there is another dataset called Ultra Feedback, right? I think some of the models use this. they have a diverse set of tasks and different LLMs for generating voice, GPT, Llama, BERT, right, and Alpaca and stuff like that. And they use GPT-4 for this preference, for getting the preference, whether Y plus is preferred or Y minus is preferred, right? So this is more of an RLHF. This is RLHF. Okay. You can actually do even better. You can use Anthropic's policy. So Anthropic came up with this constitutional AI where they came up with 16 different principles, right, and taught the models that okay, you should follow these principles, right? Let's say and this is mostly useful when you want your model to be more faithful, more unbiased, more non-toxic, right? Let's say you ask the model how to hack my neighbor's internet, right? And the model produces something. Now you say that look, let's say the model produces two responses, Y1 and Y2. Then you ask the model again through prompts that which of these assistant response is less harmful, right? Let's say your model says that in order to hack your neighbor's Wi-Fi, you do this, you don't do this, and you follow this process and stuff like that. The other response is you should not consider hacking your neighbor's Wi-Fi because this is unethical and stuff like that. Okay. Now you ask the model itself that which one to choose among this Y1 and Y2. Choose the response that is more wise, ethical, polite, friendly, and stuff like that. So now between these two, the model will definitely understand that okay, this should be Y2 is preferred than Y2 or Y1, and then based on that you give this as a feedback to the model again through prompts, okay, through prompts, and the hope is that the model will keep refining itself over the iteration. So it's a nice paper. You should look at this paper, Constitutional AI by Anthropic, and you will see all these 16 different principles. So let's now discuss about reward maximization objective. We have almost set the stage. The final touch up, the final touch up is remain. We have this reward model R, right, which we have just discussed. Given a prompt X, it will and output Y, it will generate a number, right? Now, what is our task? Our task is to essentially, let me draw this figure again. This is R, this is my policy, right? Okay. So my task is to find the optimal policy, meaning my task is to fine tune the policy LLM again and again based on the rewards feedback or the feedback obtained from the reward model, right? So that it will be able to essentially cater to the human feedback that that was used to train this model, right? So now here there is an interesting point or interesting aspect that one should consider. So if the task is to, now remember, what would be the optimal goal of this policy model? This is the policy model. What is the optimal goal of the policy model? The optimal goal of the policy model will be to generate outputs such that its corresponding reward will be maximum. So the model will generate outputs in such a way that its corresponding reward will be maximum. So what would end up happening is that the model, the LLM, the policy model will start hacking the reward model. What does it mean? It means that it will only learn how to get reward, how to maximize reward. Okay, and in a classroom setting, essentially the student will only learn how to get good marks in the exam, but the student will not learn the underlying concept as such. It is similar to that, right? And there are different ways to get good marks, right? Like, I will not discuss all these things, but here in this case, let's say the model knows that, okay, if I write a verbose response, right, a paragraph response, instead of writing a concise response, or if I use emoticons, right, if I use special symbols or Greek symbols here and there, right, so it is likely that I will get good reward. So it will try to hack the reward model. In order to address this, what is important is that, now remember, let's say when the entire process starts, right? So we start from a basic or the base policy model, let's say pi theta 1, right? You incorporate some feedback, it moves to pi theta 2, right? Pi theta 3, and so on and so forth. And then let's say finally pi theta star. And of course, pi theta star would be much better than pi theta 1, pi theta 2 in terms of reward maximization, which is the only objective that we discussed so far. It may happen that this guy will start producing responses which would just get maximum reward, but which may not look like a human generated response. So many emoticons, right? Or the answer may not be precise, may not be faithful, stuff like that, right? So, it basically reminds me of, my high school education, right? Secondary, higher secondary. So 10th standard, 12th standard. There, my friends used to say that, let's say, if you don't know any answer, any question, answer of a question in exam, you just write something, right? You just fill the entire page. You write something interesting. Try to fill out the page. Don't keep it blank. Okay. Versus, let's see, if somebody knows the answer, he or she will write a very precise 1 or 2 line sentences. And God knows, maybe the examiner will not look at the correctness of the answer, but look at the volume of the answer, and based on that, the marks will be given, something like that, right? So we'll try to hack the examiner's mind, okay, which is not the objective here, by the way. So in order to cater to that, what we do, we will also restrict the model, the final model, to deviate far from the initial state. We will not let the model deviate from more from the initial state. The model will keep updated, but it is not that it will be very different from the initial model, right? So for that, what we need a reference model. What is a reference model? The reference model is the initial state of the policy model. Let's say pi theta 1 is my reference model, and I want that, so this is pi ref, and the hope is that my final model should not be very different from the reference model. Okay, so how many objectives do we have? We have 2 objectives. One objective is we maximize the reward, and the second objective is we don't want the model to be deviated from its initial state, essentially. So maximize reward is essentially maximizing this r, x, y. Now remember, when I say that I want to maximize the reward, I always say this from expectations point of view, right? Expected reward, remember this. It is because responses are all non-deterministic, and given a prompt, there can be millions of such responses, right? So what we are interested in computing something called the expected reward. What is expected reward? Given a prompt, you give this prompt, write a poem. The policy model will generate outputs. Now these are y1, y2, y3, ... right? Every output is fed to the reward model. The reward model will produce a score. For this poem, this is the score, reward score. For this poem, this is the reward score. For this poem, this is the reward score, right? And what is the expected reward score? The expected reward score is just the average of all the rewards. So we write in mathematics, we write in this way: expectation of the of the output generated from the policy, what is the reward, and this should be high. Okay, and when I say that that two models, let's say the reference model pi ref and the final model pi theta, they should not be very far from each other. We will use a metric called KL divergence. I mean, all of you know, right? This is a KL divergence essentially measures the difference between two distributions. Remember, pi theta, pi ref, they are essentially distributions. Language models are distributions, right? They produce distributions over outputs, over tokens. So we measure the KL divergence between the reference model and the current model, and I mean, in the expectation term, it is essentially log of pi theta y given x and log of pi ref y given x, right? So what essentially you are doing, given an x, you generate y, right, through policy. Your policy model will say, right, your policy model, remember there are two models, reference policy model, current policy model. Your reference policy model will say what is the probability of y given x. Your current policy model will say what is the probability of y given x, right? You take the log of this ratio and you take the expectation, because there are many such y's given x, right? This is KL divergence. And what is our objective? Our objective is to minimize this, maximize this, okay, and minimize this. Okay, so maximize the expected reward, minimize the KL divergence, right? And in order to balance these two things, I will use a scaling factor, lambda. The scaling factor essentially says that, okay, I would like to give less weightage to the KL divergence, right, or more weightage to the KL divergence and stuff like that. So this is the final objective function, okay, for RLHF. So expectation, given this pi theta, we generate y, the reward which we want to maximize. So this is the objective function which we want to maximize. So maximize the reward, and this minus, we minimize this KL divergence. Okay. So next day we'll discuss more about this, and next day we start from here. Okay, we'll say that, okay, this is my reward model, this is my KL divergence part, and this is the combination of this. This is my objective function, and from now, how essentially we can use this objective function to update the policy model. Okay, thank you.